Okay. Because of the closure of the Gulf Park campus going on for one more day and expected to reopen on Thursday, I didn't want to have a situation where students at one campus were able to participate live while students at the other campus could not. So what doing here is just pre-recording this lecture, so it's the same presentation for students at both campuses. So what I'm going to do is cover section 5.1 on eigenvalues and eigenvectors. As far as homework assignments, the next due date for an assignment is from section 3.1 on Friday, November 6th. A lot of you have done this assignment already, but unlike past homework assignments, all assignments going forward will have no late penalty whatsoever. So effectively, it makes the due date advisory at the most. So I would recommend trying to still make it by each deadline, just so that you don't fall behind. But if you want to take a little more time on assignments that are coming up due soon and catch up on other ones later, you're welcome to do that with no penalty or consequence whatsoever. Okay, so let's get to today's section. I'm not sure why it's not letting me share the screen for this. Okay, let's go over desktop. Okay, it's still not letting me. Hold on. Okay. So what we're learning about in chapter 5 is eigenvectors and eigenvalues. So first I'm going to define those things. So what we're dealing with as a determinant is a square matrix. So A is an n by n matrix. So if you have an equation satisfied of this form, where x has to be a non-zero vector, that's extremely important. X is a non-zero vector, and lambda is just a number. So what's happening here is on the left side you have matrix vector multiplication, whereas here you just have scalar multiplication of a vector. So if those two operations give the same result for some non-zero vector x and some scalar lambda, then we say that x is an eigenvector of A, and lambda is the eigenvalue that corresponds to the eigenvector x. So really we have a pair, an eigenvalue eigenvector pair. So anytime you have A times x equals lambda times x, x is an eigenvector of A, lambda is an eigenvalue of A that is corresponding to x. Now, notice I've indicated that x can be a complex vector and lambda can be a complex number. So even if a matrix A has entries that are all real numbers, it is possible that lambda and x may be complex. Okay, now if I take this equation, ax equals lambda x, and rearrange it so that I have everything on one side, 0 on the other side, then I have a case where I have a matrix, A minus lambda identity, times a non-zero vector x is equal to 0. So this is a kind of homogeneous system that we've been dealing with before, matrix times x equals 0, where x is non-zero. So this system has a non-trivial solution. So what that means is that this matrix, A minus lambda identity, is not invertible, which is equivalent to saying that its determinant must be equal to 0. And we're going to use that later in this chapter to be able to figure out how to compute all the eigenvalues of a matrix. So because we have matrix times this vector x equals 0, then the vector x is in the null space of this matrix A minus lambda identity. So that means that it's not unique. We've seen that anytime there's a non-zero vector in a null space, that it's not unique, but you can take any multiple of it, and it's still in a null space. So what that means is if you have an eigenvector of a matrix A, any non-zero multiple of it is also an eigenvector. Now, in this section, we're not going to be dealing with how to compute eigenvalues of an arbitrary matrix. That'll come a little later. But there's one case particularly easy to get the eigenvalues, and we'll make use of this. If a matrix is triangular in any sense, if it's lower triangular or upper triangular, then that reveals the eigenvalues that are just the diagonal entries. An n by n matrix A generally has n eigenvalues, although those eigenvalues are not necessarily distinct, but there are at most n distinct eigenvalues. Okay, so now let's get into the problems. So for this first one, we're given this vector 2, 0, 1, and we're given this 3 by 3 matrix A. So the question is this vector an eigenvector of this matrix? So that's something that's actually fairly easy to check, because all you have to do is go ahead and carry out the product A times V, because it's an eigenvector if we have a situation like this, like A times V is a number times V. So we go ahead and compute this left side. So A times V, the matrix vector product, is computed here in the usual manner. So I'm going across each row and down this column, multiplying and adding as I go. So minus 1 times 2, plus 0 times 0, plus minus 2 times 1 gives the first entry, and then 2 times 2 and 5 times 0 and minus 4 times 1 gives a second entry, and so on. And I go ahead and compute all of that, and this is what I get, minus 4, 0, minus 2. So what you do now is you compare this to the original vector V. Is A times V a scalar multiple of V? And you can see that it is, because all I have to do is take this vector, multiply it by minus 2, and I get this vector. And that's what we see here. A times V is equal to minus 2 times V. So what it tells us is V is an eigenvector of a matrix A. And the number you're multiplying it by to get AV, that's minus 2, that is the eigenvalue. So minus 2 is an eigenvalue of A, and 2, 0, 1 is a corresponding eigenvector. All right, here's another problem of the same kind. Is this vector an eigenvector of this matrix? So we go ahead and compute A times V, so standard matrix vector product, and we get this, 7, 6, minus 7. And if we compare this vector to this one, we see that it is definitely not a scalar multiple of V, because that would require that first entry must be twice the second, which is not true. So as soon as you have something like that not hold, then you know it is not an eigenvector. Okay. Here it's asking a different question. It's asking if lambda equals 8 is an eigenvalue of this matrix. So we're not given anything related to an eigenvector. If it is an eigenvalue, then we need to find an eigenvector. So a given number is an eigenvalue if and only if this system, A minus lambda identity times V, has a non-trivial solution, because that would mean that A times V equals lambda times V. So what you do is you form the matrix A minus 8 times identity, because we're looking at lambda equals 8, and get this matrix here. This is a matrix that has to have a non-trivial solution when set equal to 0, or when this type of vector is equal to 0. So we're going to row reduce A minus 8 times identity, And to see if this system is a non-trivial solution, we need to see if we end up with a free variable once we carry out the row reduction. So we perform row operations. First, I just negate the first row, just so I have a 1 here, just for convenience. And then I use this first row to eliminate the entries in the first column that are below it. So 4 times row 1 from row 2, and then adding twice row 2 to, I'm sorry, this is a typo. That should be R1. I will fix that when I post these notes in Canvas. So row 3 is equal to itself plus twice times row 1 to eliminate the -2 down here. And then I negate the second row, just to have a 1 here, again for convenience. And then I subtract 3 times row 2 from row 3 to eliminate this entry. And we see that the third row is all zeros. So we end up with the third unknown, V3, is a free variable. So that means that system of equations of this matrix times V is equal to 0 has a non-trivial solution. So what that means is lambda equals 8 is an eigenvalue of the original matrix. Okay, so now we need to solve the system of equations implied by this matrix to get a non-trivial solution and a vector. So we have a free variable v3 corresponding to this column. So you got to set something non-zero to get a non-zero result. An eigenvector must be non-zero. So I set it equal to 1. So now I use this equation to solve for v2. So this says that v2 is equal to 3v3, because remember, you're moving this to the other side. So v2 is equal to 3. And then we go to the first equation. We have v1 minus 3v3 is equal to 0. Again, move this term to the other side. So I have v1 is equal to 3v3. Therefore, it is also equal to 3. So that is our eigenvector, 3, 3, and 1. But any non-zero value substituted in for your free variable will do. But then it would be a vector that's a multiple of this one. Okay. Similar kind of question, is a lambda equal 8 an eigenvalue of this matrix? Again, find an eigenvector. So we carry out the same process. Take the matrix minus 8 times identity and obtain this matrix. But that's the matrix of this homogeneous system. So we need to row reduce this to see if there's a free variable, and if so, this system would have a non-trivial solution, and therefore 8 would be an eigenvalue. So we carry out the row operations. So first I divide the first row by -2 to make this a 1. And then I use twice row 1 to eliminate this entry from row 2, this 2 right here. And that brings me here. Then I divide the second row by -3, just to conveniently get a 1 up here. We see that the second and third rows are the same, so you just gotta subtract them, and that wipes out the third row. So once again, we have a row of zeros. We have v3 being a free variable. So the system has a non-trivial solution. Therefore, lambda equals 8 is an eigenvalue. So we again set our free variable equal to 1 to get a non-trivial solution. So I use this equation. This says v2 is equal to 2v3. Again, you're moving this to the other side. So v2 is equal to 2. And then I have v1 is equal to v1 plus, sorry, let me repeat that. v1 is equal to v2 plus v3. Again, these two terms are moved to the other side. And we substitute in 1 for v3 and then 2 for v2. And that gives us v1 is equal to 3. So that gives us our eigenvector, 3, 2, 1. Okay. Finding the eigenvalues of this matrix. It's actually very quick to do in this case because this matrix is upper triangular because all of the entries that are below the main diagonal are equal to 0. So when a matrix is triangular, you can just read the eigenvalues off the diagonal, 0, 6, and 4. That's all that's asked for in this problem. So we only know how to handle triangular matrices at this point, but in the next section, we'll handle more general case. Now, in some cases, you can find an eigenvalue just by looking. Triangular is one case, but there are other cases too. Because we have a matrix like this where we notice that all the rows are the same. So when you have a matrix where all the rows are the same, or even if they're just scalar multiples of each other, that's a matrix that is not invertible. It's actually a rank 1. So when a matrix is not invertible, that means its determinant is 0. Now remember, lambda is an eigenvalue if a determinant of A minus lambda identity is 0. Well, if the determinant of A is 0, then that means that A minus lambda I, where lambda is 0, is not invertible. Therefore, anytime you have a matrix that itself is not invertible, that means that 0 is an eigenvalue. So that's something you can conclude very quickly, at least in certain cases. Here again, we have all the rows being the same. So this matrix is not invertible. A non-invertible matrix has 0 as an eigenvalue. But what it's asking for in this case is, don't just find an eigenvalue, find 2 linearly independent eigenvectors of A. So to find any eigenvectors, what you need to do is take A minus lambda identity and row reduce it. Well, lambda is 0. So really we're just taking A and row reducing it. So if I were to, I could just subtract row 1 from row 2 and also from row 3. That makes rows 2 and 3 equal to 0. And then for convenience, I can divide the first row by 2. So after row reduction, A is reduced to this matrix. It has 1s in the top row, and then all of our rows are 0. So here we have 2 free variables, v2 and v3. And all the unknowns satisfy this equation. So I can set v2 and v3 to equal to 2 different combinations because I need 2 linearly independent eigenvectors, and then I can solve for v1 to finish it off. So for first eigenvector, I set v2 equal to 1 and v3 equal to 0. So when I substitute both of these values in here, I solve for v1 and I get -1. So that is an eigenvector. Now I need another eigenvector that is linearly independent of that one. So what I could do is I can set v2 and v3 equal to values that are linearly independent of these. So I set v2 equals 0 and v3 equal to 1. And I substitute both of these values into this equation again. And again, I get v1 equal to -1, so that is my other eigenvector. So these 2 eigenvectors, we can see that they are not scalar multiples of one another. So these are 2 linearly independent eigenvectors of A, corresponding to the eigenvalue of 0. So these actually describe the null space of A. Last problem, construct an example of a 2x2 matrix that has only one distinct eigenvalue. So here we can use the fact that the eigenvalues of a triangular matrix just come from a diagonal. So what you could do is make a matrix that's triangular. So I happen to choose upper triangular. And then since the eigenvalues will sit on a diagonal, I just have to make the diagonal entries the same so that there's only one distinct eigenvalue. So I put 4s on a diagonal. And then it doesn't really matter what you put after that. If you're going to make it upper triangular, you have to have a 0 down here. And then you can put anything you want up here in the row 1, column 2 position. So I just put a 5. So this is an example of a 2x2 matrix where the eigenvalues come from a diagonal because it's triangular. And since both diagonal entries are the same, then there's only that one value as the one and only distinct eigenvalue. So that's it for the problems from this section. So we'll learn more about how to compute eigenvalues of an arbitrary matrix in the next section.